Okay, so let's start. We'll continue our discussion on divide and conquer. So we already saw many examples. We saw binary search, powering an integer, and integer multiplication. And yeah, we'll see the fourth example today. I think I introduced this example to you, matrix multiplication. So we will need this problem later also for designing algorithms for solving that problem. So this is a very important linear algebraic problem with tons of applications. Basically, you need in every area you to multiply matrices. So the definition is simple. We are given two n cross n matrices A and B, and we need to output the product of these two. So let's say the entry in the ith row and jth column is ij, and the ith row and jth column of the entry is bi. So this is how the two matrices are defined. They're all n cross n matrices, and we need to output the product of these two. Right. Right. So how this multiplication is done is, if you want the entry in the first row and first column, C11, you just multiply the first row of A multiplied by the first row of B, first column of B. Similarly, for C12, you multiply the first row of A multiplied by the second column of B. Okay. Okay. And you keep on doing this to get the individual int. Okay. And this is how you get C11 is A11 multiplied by B11, A12 multiplied by B21, A1 multiplied by B1. And similarly for Cij, you get this particular expression. AI multiplied by B1j, AI2 multiplied by B2j, and you just add this. So in general, if you want the ijth entry of C, you'll take aik, k ranges from 1 to n, aik multiplied by b. So this is fairly straightforward algorithm. And how much time does it take? So there are n many additions happening for each entry. There are n square many terms. We need to figure out the running time is n. Okay. This is a straightforward algorithm. You have this matrix multiplication AB for I from 1 to n, for j from 1 to n, set it to 0, and then add it by aik multiplied by b. Right. There are 3 loops, each iterating n times, 30 times n. Okay, so this is straightforward. And we were trying to improve upon this algorithm using divide and conquer. Okay. So the obvious question is, can divide and conquer help us to better? And we get better than integral. Okay. And there was one approach we saw. Partition each of these matrices A, B, C into 4n by 2 cross n by 2 subgroups. Okay. So you draw a line in the middle and draw a horizontal line, draw a vertical line. So the top left half will be one part, the top right part, the bottom left part, and bottom right part. Similarly, we do the same for B. right? So initially we were multiplying n cross n matrices, and now we want to somehow reduce it to multiplying 2 cross 2 matrices. Okay? And these are all small size matrices. Each of them is of size n by 2 cross n by 2. So this is our divide and conquer strategy. So we'll divide it into 4 submatrices. And obviously, why are we going over 2 cross 2 is because this is the easiest case of multiplying this matrix. You could try different things like 9 n by 3 cross n by 3 matrices, but that will obviously just give you I think slightly worse run. So in fact, convince yourself that this is the best strategy. Okay? So this is the way we split A11, A12, A21, A22, and we just multiply these matrices. So what will be C11 will be A11 into B11 multiplied by A12 multiplied by B21 and so on. Evaluating this, we get these 4 equations which we need to solve. Right? So in one step, you get the top left uh, part of this matrix C. And what is happening here? So there are 8 matrix multiplications, each of size n by 2. And then you are adding some things. So how much time does adding 2 matrices take? Let's say I want to add n cross n matrices. Yeah, n square, because each entry will take constant time and there are totally n square meaning. Okay, so we got this, and this is just the pseudo code for this cell. Partition ABC into 4 submatrices of size n by 2 cross n by 2. Evaluate this and return the final matrix C. So what we will do here is that we have 8 many matrix multiplications, each of size n by 2 cross n by 2, and the adding part that took order n square time. So that's the recurrence. Tn equal to 8 Tn by 2 plus order n square. And we know how to solve this kind of recurrences. You could use the master theorem or whatever recursion tree method. And it is easy to see that this recurrence has solution n. This will be n by 2 whole cube multiplied by 8. Yeah, very easy to see this. So we have not got any improvement. Initially, the brute force, where we just expanded out the matrices, that also took any time. This also took any. And yeah, so what other divide and conquer things can we do?
Hello, sir. I have a doubt.
Yeah,
Sir, in any programming language, how we can split the matrix into 4 other matrix? Because there should be a function
there
like
should be a function. So what is
here.
my, yeah,
You return that A11 B11, but it is A11 and B11 itself are matrix. So how we can extract from original matrix to this and we can make this matrix like.
uh, so what all you need to do? First, you have this A matrix, right?
Yes.
From that, you construct these 4 submatrices of size n by 2 cross n by 2.
But sir, in any programming language, how we can construct?
Now,
Because
why can't you?
we should know
Uh,
the index of
yeah, you know the
the
index. So, what is the top left thing? A1. So, you are looking at columns n by 2 and you are just restricting these rows to n by 2, right?
mm,
Similarly, you can do for A12. A12, what do you get? So, this index n by 2 to n and this columns 1 to n by 2. And you just
mm.
extract out those entries and specify this matrix accordingly.
Okay, so here there should be some mathematical formula to calculate the index means.
Okay, if you want to look at that way, but I think once you know how to give A as input, right? So how will you give A as input? You will specify all the entries,
Mm.
A11, A12, and so on. Right?
Yes.
And from that you need to construct this matrix. So you just take whatever entries you need and put it in this matrix.
Okay, sir, I will try to
Okay.
construct.
So actually, generally, this matrix multiplication things, there are softwares for that. You can do it using MATLAB, and where it is much easier to input this matrix. Okay, next, so we need to improve upon this order and cube algorithm. And obviously, the natural idea is can we reduce this number of multiplications? We needed 8 multiplications here. Can you reduce some? So this was a major open problem for many years. And a lot of people tried to improve. So this was in the late 1800s or so. A lot of people tried to improve n cube, and at one point, people thought that n cube is the best you can do. But then there was one nice algorithm by Strafford, showed that you need not do 8, but you can do with even 7 multiples. Okay? And he took almost, so the final, if I show you the description, it is very easy to verify and this thing, but it took almost 10 years to reduce this 8 to 7. And I think you can't go below 7. There are some lower bounds. You can't do Pn equal to 6 Pn by 2 parts, something like that. So to improve upon that algorithm, it will take for some advanced techniques. And it is still a very major area of research. Matrix multiplication can you improve the running time? So what we believe is that you can, for any epsilon, you can get an n to the 2 plus epsilon algorithm, but nobody knows how to do it. Right? So yeah, how do you reduce the number of multiplications? So it's some very mysterious calculation done by Strassen. It was a major breakthrough when this algorithm actually came out, 1969. So we'll see some. So this is all the calculation he did. We'll try to understand what exactly he did. So these are our 7 multiplications. Okay. So the first one is A11 into B11 minus B2. Okay. Is A11 plus A12 multiplied by B2. A21 plus A22 multiplied by B1 and so on. Okay. Now our goal is given this, you need to add some things, subtract few things, and finally arrive at our goal. which is we want to compute C1. Right? So what is C11? Is A11 multiplied by B11 plus A12 multiplied by B2. So I give you these equations. Can you figure out how to calculate C1? Okay, here is the answer. E1 plus E4 plus E5 plus E7. So, what do? Take E1, A11 B11 minus A11 B2. Okay. Let me just read that in. Okay. So, in fact, it is difficult to figure this out. And here is one example, which is E5 plus E4 minus E2 plus E4. Okay. So, what is E5? A11 plus A22 multiplied by B11 plus B2. And then you similarly compute this E4 plus A22 B21 minus B1 minus A11 plus A12 B2. A12 minus A22 B21 plus B2. And this is the sequence. And finally, what do you get? You just expand the first term, A11 B11 plus A11 B22 plus A22 B11 plus A22 B2. And many terms will get cancelled out. And for instance, here A11 B22 is getting cancelled with this term. A22 B11 is getting cancelled. A22 B22 is getting cancelled here. A22 B21, and finally what you get is A11 B1 plus A12 B2. Okay. And in fact, coming up with this is far from easy. Like, even to verify, you are need to think for a lot of time. So coming up with these calculations is very easy. And in fact, most people don't know how we figured this themselves. So, but a rough idea is that he's trying to multiply uh, sort of the diagonal integers, okay, B11, A2. So he has added some terms and subtracted some terms from somewhere. So he wants this to cancel out with something else.
Sir,
Okay.
sir, sir,
Yeah.
here for each step we are reducing the number of multiplications, but
Yeah.
for computing the GIs we need to add and subtract also. It is enormous amounts of addition and subtraction also. So
Yeah,
would
that
it
is
take
right.
some time and compensate for the time that was saved from multiplication of 8 element?
Yeah.
Because it is
So,
for each
so
step many additions and subtractions are also taking.
yeah, sure. No problem. So how much time do you need for this addition?
So it is order of n square by 4 or n
Yeah,
square
exactly.
for each addition and
Yeah,
subtraction.
sure. For each addition, we need order and square. So the main point to notice is that the recursion is the same. So what is the recurrence for this algorithm? How many multiplications do you require? There is just one multiplication in every equation. There are 7 many equations. So it's 70 n by. And how many additions do you require? Again, there are just two additions here. And, but overall, the point is that there are only constant number of adding of matrices,
Yes, sir. Yes, sir.
right? Here you have,
Means
yeah.
for each step, same number of addition and
No, not same
subtraction.
number of addition. Like here you need to add two different n by 2 cross n by 2 matrices. Here you need just one addition. Yeah. So anyway, what is it? 2, 2, 2, 6. Is this true for only square matrix? Yeah, that is an interesting question. But yeah, you could do it for any rectangular matrix as well. It's just you can add a bunch of zeros to make it square. Yeah, so it doesn't matter what matrices we are talking. You can always do any matrix multiplication using this algorithm. So it is sort of what is called as padding algorithm. Even if you have rectangle, you can easily make it square by adding zeros at appropriate locations. Okay, what about the next one? C12. This is also difficult, I guess. No, it's easy. Just E1 plus E2. Okay, anyways, just think about this. There's some typo here. Convince E1 plus E2. What was our E1? Okay, so let's just leave this part out. Let's look at E3 plus E4. What do you get? A21 B11 and plus A22 B1. Okay, A22 B11 gets cancelled out here. So you get A21 B11 plus A22 into B21. Right? So this is fine. What about this computation? E5 plus E1 minus E3 minus E4. Can someone quickly compute it? So you have E5 plus E1 minus E3 minus E4. So I think this should be B1 too. I believe it should be B1 too. Okay, anyways, so let's just move on. Let's verify these computations. E5 plus E1 minus E2 minus E. And mostly this should work out. So there's 7 multiplications, each of size n by 2 cross n by 2. And what's the running time? Needed some theta n square for additions.
Order of log 7 to the base 2.
Yeah, log 7 to the base 2. And if you look at that, it's something 2.88. Okay. It's a minor improvement, but it is something 2.80. So overall, it's just n cubed to n to the power 2.8. But I think for n larger than 32 or something, this running time is much better. Okay. So this is still a very active area of research. So there are all these improvements, but we are just focusing on this Strassen's algorithm because it is easy to describe and doesn't require any advanced concepts. There was one by Victor Pan, he moved it to 2.796. There was another by, I think this was Strassen and Schoenhage, 2.522. And Romani then moved it to 517. 496 Coppersmith and Winograd. This is a very nice and famous algorithm. And then Strassen again came back. He would introduce some laser method of matrix multiplication, improved it to 2.479, 2.376, again by Coppersmith and Winograd. And after that, there was a long break. People were not able to improve this. And we are sort of saturating now. 376 it went to 374, and then it went to all this 3728642, 2.372863 legal and degrees. Okay, and in fact recently also there was some improvement, but I'm not sure. So actually this might say why are people spending so much time on this problem? So in fact, we'll see later in the course that we will need to apply this matrix multiplication algorithms for a wide variety of other things. Like, let's say if we know a bit of graph theory or given vertices, edges, we want to find the distance between two nodes. Okay. So there you can formulate it as a product of matrices. Just think about it. Interesting reduction. Okay, so this is about the upper bounds. What progress has been made on upper bounds. I think the best lower bound is just n square log n. Okay, but the only thing is that it requires real or complex value. For integer matrices, we don't know. It's just n square lower bound. So we are far from bridging this gap. We don't know how to do it. So later in this course, we'll also see how to do interactively. All our standard techniques won't work for certain problems, so they are difficult. And how do you show that they are? So we don't have any technique for saying that all algorithms fail to achieve this result. So generally, what we do is that we try to use that better algorithm to design better algorithms for certain other problems. Then we say that we don't believe this, so we don't believe that this particular boundary. Okay, this is about matrix multiplication. So, is there any question about this? Okay, so this is a nice linear algebra. We move on to some other applications of divide and conquer. And
Sir,
yeah,
sir, I had a small doubt. Sir, in the
yeah,
recurrence relation that we formed, P of
yeah.
n is equals to 17 by 2 plus order of n square. Sir,
Mhm.
here n should be the number of elements of the matrix or
No,
should
no,
it be the
number of rows.
number of,
Number of
and
rows.
it is the
So
order
it's,
of
yeah,
matrix.
yeah. So n cross n bit. We are dealing with. Yeah.
Oh, okay, sir, okay. And sir, how do we get this recurrence relation?
So what are we doing here? Look at this element. We are applying divide and conquer. We divide it into four parts. A11, A12, A21. Each of these matrix, what's its size? N by 2 cross n by 2.
Yes, sir.
Right? And in every this expression, we are just applying one multiplication. Right? So you are multiplying 2n by 2 cross n by 2 matrix. So that's how 70n by 2 came. Okay? There are 7 multiplications, each of size n by 2 plus n by 2. And there are some additions also we are doing. How much time each
And that,
addition take? Yeah,
yes, sir,
beta
and
and
that overhead is from the additions and subtractions, order of
yeah,
n square.
addition.
Yes, yes, understood, sir. Yes.
Yeah. Okay.
Thank you, sir.
So that's how we get this 10 to 2 pointed. Okay, so let's move on. Now we'll look at some array problems. That was linear. We want to solve some array problems using divide and conquer. Okay, so you are given a set of n unsorted numbers. They are in any arbitrary order, and we want to find the kth smallest number. Let's say you are given this array. There are these numbers 2, 5, 8, 4, 6. 2 is the smallest number, 4 is the next largest, 5 is the next largest, 6 is the next largest, 8 is the next largest. And I'll just give you an input k and tell me the kth smallest number. So how will you solve this?
So, sir, here what I think is we can use a merge sort technique of partition and check
Yeah,
the index.
yeah. So that is one way, but it just okay. We can take that, but what is the most obvious thing you can do?
Sir, we can first sort it and then
Yeah,
return the
exactly.
integer at kth place.
Yeah, exactly. So we'll just sort this array that will take n log n time and just output what is the case. And there are some specific examples which are most interesting to us. One is the minimum, maximum, and what is the central element, which is called the median. Okay. So let's just look at these simple cases and then we will move on to other. So minimum, how do you do? So how much time do you need for finding the minimum?
Order of n.
Yeah, order. So we are looking for better than the sorting algorithm. Sorting takes n log n. So minimum and same for maximum. You just need order of n. Okay. Now let's consider some restricted things. Yeah. Let's say I tell you I want to compute the maximum, but I am only allowed to add these numbers or take their minimum. Okay. And now I tell you what is the maximum amount. Yeah, you can use whatever you want, heap, sort, or okay. But right now I'm just interested that I'll just allow you to use minimum. Um, Minimum and addition.
So can you please repeat what?
Yeah, so I want to find the maximum among these numbers. But the only operations I am allowing is you can add two numbers or you can take their minimum. Is that clear?
Yes.
Sir, we can add first number with every number and the in whichever the sum is maximum, we will consider as it makes.
So you will add first number with every number. So you are summing up everything.
Yes.
Okay. And then
And
what do
then
you
the
do?
maximum sum, whichever will be the maximum sum, that index will be our max element.
Um, no, so what do you do here? 8. Okay, so you want to figure out how do you compute 8. So you sum 2 plus 8 plus 4 plus 6.
No, sir, like
No.
2 with 5, then 2 with 8, 2 with 4, 2 with 6. So whichever sum will be the maximum, that will be our the max
So
term.
here it is 10.
Yes.
And then what do you do?
No means
But
2
sir, I
times.
guess we don't have the maximum function. No, we are not allowed to use maximum, right?
Yeah, you are not allowed to use max.
Okay, sir. Then I can.
Otherwise, it is trivial. Yeah. And we don't have max. That's the problem here.
So we can find the minimum and leave the number which is minimum aside and take the other one and continuously compare for minimum.
Sorry, your voice was breaking.
We can take the first, like we can compare 2 and 5, and out of that minimum is 2. So like I will
Yeah,
discard 2, I will take 5.
you will take 5. Okay.
Now I will compare 5 and 8. So like
Hmm.
5 is minimum. So I will
Hmm.
discard 5 and keep 8 with me. So like
And keep it
doing
with.
this, we can
Oh,
go through whole of the array or whatever we have. And at last operation also, we will just do the same thing. If we get the minimum one, we'll discard the minimum one and other one will be our maximum term.
okay. So you don't need additions here. You just
Like
apply minimums.
in this method, I don't need addition.
Okay, this is a good solution, but I was sort of looking for a formula which you can tell me instead of this discarding approach. Yeah, can you hear me? Okay, so I will just tell you one solution. 25846. No, so everybody is telling me take the maximum of this, and so the thing is I don't have maximum. I just have minimum and plus. So the thing is that you can't do with just minimum and plus. You will need minus also somewhere. Okay, you try to prove that just using minimum and plus you can't come find out the maximum. And so here is one solution. I'll just add all these numbers. 25846. So what is it? 7, 8, 15, 19, 25. Okay, store 25. And then you just add 4 numbers for all 4 choices of these numbers. Okay, and take the minimum of all. So one is 2 plus 5 plus 8 plus 4, another is 2 plus 5 plus 8 plus 6, and so on. 2 plus 8 plus 4 plus 6. Okay. And you take the minimum sum of all of those. So 2 plus 4, 6, and 5, 11, and 17. Okay. So 17 will be the minimum. And from the 25, you deduct 17, you get 8. So this is one algorithm. And in fact, you can also show that if you are only allowed these operations, minimum plus and just to a single subtraction, then this is the best you can do. But we'll not go into those details now. Okay. Let's move on to something more interesting. So we saw how to compute the minimum, we saw how to compute the maximum. Now the question is median. Is the center element. So what should this uh, central element satisfy property? That equal number of numbers are less than this element and the same number is greater than this element. Okay. So what is the central element here? Median. It is 5 because 2 and 4 are smaller than 5, 6 and 8 are larger. So how do you figure out this 5? Yeah, that's what we want. But so you would have seen this algorithm, partition algorithm, and how does it work? For instance, in quicksort, how do you solve it? You just find some element and such that you need to partition the array suitably so that it's sort of the central element, median element. So you would have seen this in data structures course or whatever. Uh, okay. So we need to generate a good split element X and then recursively find the required element. So this is our subroutine. We want to partition it into two subarrays around this pivot element X. So initially we start with some pivot element and you reorganize the array such that all elements less than X are to the left of this X and all elements greater than X are to the right. So this is how the array should look. And of course, so the main challenge is how will you find this central element and how do you partition this in linear time? We already had some n log n algorithm. We want the order n.
Sir, can I say?
Yeah.
Sir, first of all, we will choose X and then traverse through the array, and whichever elements are less than x, that will be put in the array, that will be put in the left sub array, and whatever the elements are more than x, they will be put in the right sub array with means that partition with elements that are more than x. So
Okay.
it will take order of n time.
Yeah, this is okay. But you sort of need some extra space on this in addition to the input array. So you will create some left sub array, you compare each element with x and put it there.
Yes, sir. The space will be required for.
Yeah, space will be required. So, and can you switch some elements here so that inside this array only I get this form where I have x in the middle and less than x and greater than.
But sir, choosing that good X should be there,
Yeah,
no means.
yeah, it is difficult. Yeah, I understand that.
Yes.
But we are not worried about that, no, because we don't have the time to do all that. I just want to say, let's say I give you some x. Okay? Uh, I want to split this array such that all the elements which are less than x, that will be to the left side, and all the elements which are greater than x are right side. So basically what I'm saying is you swap some two elements and can you transform any given array into this?
Sir, here we can take two variables, first pointing to the starting point and another pointing to the ending point, and just like quick sort, we can swap.
Yeah, so that is what this partition algorithm quick sort does. So this is our start element P and this is our ending element R. So you start with x equal to AR, I is set to P minus 1. And let's say this is what I decided as my pivot. Okay. X is the end. And you keep on comparing it with X and if it is less than x, then you swap some adjacent values. And like this is finally what you will reach is, and I is getting incremented, and so you finally just swap the ending element with the start. Right? So let's just see. So all these operations, so they take constant amount of time. You are just swapping, you are adding, you are comparing, or you are just setting this value. Okay. And overall, it is easy to see that this just takes order and time. Okay. So let's just see one example. Let's say I have this array 3621754. Right? So this is what I want as my pivot 4. Okay. So first you compare this 3 with 4. 3 is large, smaller than 4. So this will stay as it is. Okay. Then you compare this 6 with 4. Okay. So that is not true. Then you go over this next element. 2 is less than 4. So obviously, so you just have to need to use your common sense. So this 2 will keep on moving towards the left because it is less than 4. And 6 will obviously move to the right. Okay. Again, you start comparing again. So now you move on to 1. Again, 1 is less than 4, 1 will shift. 3 to 1, 6, 7, 5. And finally, you see that all of these elements are larger than this. Okay. So this is what we have. All elements less than 4 are here and all elements greater than 1. And then you just make a final swap, which is compare 4 with 6. And that is the final array. 3, 2, 1, 4, 7, 5. Okay. So this is about the how to find the middle element, and we'll see how to make a good choice of this pivot element. Okay, so that's it for today. There are any questions, comments?
Sir, can you upload these notes if possible?
Yeah. Okay, I'll stop this meeting now.